About 650 light-years from Earth, one of the most famous stars in the night sky may be hiding a secret that changes everything we thought we knew about how giant stars die. For generations, astronomers believed Betelgeuse was living out the final stage of its life alone. A massive red supergiant, swelling outward, burning through its last fuel, and slowly moving toward the supernova that would one day destroy it. That story sounded complete, clean, familiar, but it may be wrong, because Betelgeuse may not be alone at all. A second star appears to be trapped inside its outer atmosphere right now, buried within the enormous envelope of gas that surrounds it, spiraling inward little by little. It is not escaping, it is not stabilizing, and if this interpretation is correct, then this system has already crossed the point where the ending can no longer be avoided. Tonight, we are following that story from the beginning. We are going to look at the strange signals astronomers kept seeing for more than a century, why those signals may have been misunderstood, and why one of the brightest stars you can see with your own eyes may actually be in the middle of a slow-motion stellar disaster. If you step outside on a clear night and find Orion, Betelgeuse is the reddish-orange star shining from the hunter's shoulder. It looks calm, familiar, almost permanent, but appearances can be deeply misleading in astronomy. The closer we look, the stranger this star becomes. Betelgeuse is enormous. If you placed it at the center of our solar system, its outer layers would stretch outward past the orbit of Mars, and in some estimates even farther. It is one of the largest stars visible to the naked eye, and it sits close enough to Earth that astronomers can do something extraordinary with it. They can study it as more than just a point of light. They can watch its surface change. They can track its dimming. They can analyze motions in its atmosphere. And the more they observed, the more Betelgeuse stopped behaving like a simple single star. For most of the modern era, the standard picture seemed straightforward. Betelgeuse was understood as a red supergiant, roughly 16 to 19 times the mass of our Sun, nearing the end of its life and heading, eventually, toward core collapse. Massive stars do this. They exhaust their fuel, they become unstable, and then one day they explode. That by itself is dramatic enough, but recent analysis suggests something much more unusual may be happening here. Instead of dying alone, Betelgeuse may be sharing its outer atmosphere with another star, a smaller companion with roughly 1.5 times the mass of the Sun. In current discussions, that hidden companion is often referred to as Sawara. And if it is really there, then it is not safely orbiting at a distance. It is embedded inside the outer envelope of Betelgeuse itself. That is where this story turns from strange to almost unbelievable. Imagine a star so huge and so swollen that another star can move inside its extended atmosphere without immediately being destroyed. That is not science fiction. That is the picture astronomers are now seriously considering. Sawara may be orbiting through Betelgeuse's outer gas, losing energy with every pass, spiraling deeper over time. And that loss of energy is the key, because orbiting inside gas is not the same as orbiting through empty space. In empty space, an orbit can remain stable for immense periods of time. But inside a star's atmosphere, even a very thin one, drag begins to matter. It may be weak at first, but it never stops. Every orbit through that gas steals a little energy from the companion. Every loss of energy shrinks the orbit slightly, and every smaller orbit carries the star into denser gas, where the drag becomes stronger. That creates a feedback loop. Stronger drag causes faster orbital decay. Faster orbital decay pushes the companion deeper. Deeper layers create even more drag. Once that cycle begins, it becomes extremely difficult to stop. In practical terms, the system may have already passed the point where recovery is possible. That is what makes Betelgeuse so fascinating. We may not just be looking at a star that is going to explode someday. We may be looking at a system already locked into a slow inward collapse, one that is unfolding right now on astronomical timescales. And even though the final merger may still be thousands of years away, that does not make it slow in stellar terms. For stars, 10,000 years is not a long time. It is a final phase, a closing chapter That is what gives this whole story its eerie feeling. This is not a distant, abstract possibility. This may already be in motion. And before we go deeper, take a second to subscribe to the channel. We cover stories like this in a documentary style, where the biggest events in the universe are not just explained, but followed all the way to their consequences. So if that's your kind of content, subscribe now and stay with me, because Betelgeuse only gets stranger from here. What makes this even more remarkable is that the evidence may have been sitting in front of astronomers for decades. Betelgeuse is known to brighten and dim over time. That part is normal. Giant stars often pulsate, expanding and contracting in cycles. Betelgeuse has a major brightness cycle that lasts a little over a year, and that kind of variation fits what astronomers expect from a red supergiant. But there was another pattern underneath it, a much longer cycle, repeating roughly every 6 years. That 6-year rhythm kept showing up again and again in the data. It was too regular to ignore, but too unusual to explain easily. For a long time, many assumed it had something to do with the star's internal pulsations, or with giant convective cells rising and falling in its atmosphere. Others explored magnetic explanations. But none of those ideas fully solved the problem. The pulsation explanations struggled because the timescale did not fit well with what models of a star like Betelgeuse should be doing internally. The convection explanations struggled because convection is messy and chaotic. It can create irregular changes in brightness, but it should not produce a clean, repeating cycle with clock-like persistence over such long periods. Magnetic explanations ran into their own difficulties, and that left one of the most uncomfortable possibilities on the table. What if the 6-year signal was not coming from inside Betelgeuse at all? What if it was orbital? What if the repeating pattern was the fingerprint of a companion star moving through the outer atmosphere of the giant itself? That idea sounds extreme, but the numbers line up more cleanly than many of the alternatives. A companion at the right distance, moving through the extended envelope of Betelgeuse, could naturally produce a period in roughly that range. Suddenly, the weird signal starts to look less like unexplained noise and more like a warning that the system had been misread for a very long time. And if that is true, then Betelgeuse is not just interesting because it is close. It is important because it may be one of the first times we have ever been able to watch a common envelope system while it is still happening. That phrase matters, common envelope system. It describes one of the most violent and unstable stages two stars can enter together. One star expands until it engulfs the other. The smaller star ends up moving through shared gas. Friction drains orbital energy. The orbit shrinks. The system changes rapidly in stellar terms. Sometimes the companion merges with the core. Sometimes the envelope is blasted away. Either way, the system does not remain the same. That may be what Betelgeuse has become. Not a solitary giant waiting quietly for death, but a two-star system trapped in a process that is rewriting how its final explosion may eventually happen. And that changes the story completely, because once you accept the possibility that another star is already inside Betelgeuse, every strange behavior starts to look different. The dimming episodes, the atmospheric disturbances, the unexplained long cycle. Even the future supernova may no longer be the ordinary death of a single red supergiant. It may be the final outcome of a hidden merger that has already been underway for a very long time. So the real question is no longer just when Betelgeuse will die. The question is what kind of death is being prepared inside it right now. And in the next part, that is exactly where we go next. The repeating signal astronomers saw for over 100 years, why it may have been misread for generations, and how the evidence for a hidden companion slowly started to become impossible to ignore. The signal astronomers misread for a century. For more than 100 years, Betelgeuse kept sending out the same message. Not loudly, not clearly, not in a way that immediately forced anyone to rethink the entire system, but steadily, repeatedly, quietly enough to be dismissed, yet persistent enough that it never fully went away. And the deeper astronomers looked, the harder it became to explain that signal as an ordinary part of the star's behavior. By now, most people know Betelgeuse as the strange red star in Orion that sometimes brightens and fades. That much is true. Variable stars do this. Giant stars especially do this. Their outer layers expand and contract, their surfaces boil with enormous convection cells, and their brightness changes over time. None of that, by itself, is surprising. Betelgeuse has a well-known primary rhythm, a shorter cycle tied to the normal pulsations you would expect from a red supergiant. That cycle makes sense. It fits the broader picture. It tells a story astronomers already understand. But underneath that familiar rhythm, there was another one, a longer, slower pattern. Roughly every 6 years, the star repeated a second variation in brightness. Not perfectly, not with mechanical precision, but with enough regularity to stand out. Enough to be measured. Enough to keep showing up in the data decade after decade. That is where the problem began, because the 6-year signal did not fit comfortably into the standard model of Betelgeuse as a single isolated star. At first, astronomers tried to place it inside the star itself. That was the natural move. If a giant star is changing in brightness, the first assumption is that the cause must be internal, maybe another pulsation mode, maybe some deeper oscillation in the envelope, maybe giant convective structures cycling through the atmosphere, maybe magnetic activity influencing the surface. All of those ideas were explored, and none of them fully solved it. The pulsation explanation had a basic weakness. The timing did not fit well. Stars do pulsate, but pulsations are not random. Their periods are linked to the structure of the star, to its density, size, and internal physics. The 6-year cycle looked awkward in that framework, too long to sit comfortably where astronomers wanted it to sit, too stubborn to disappear. The convection explanation had a different problem. Convection is violent, chaotic, and messy. In a red supergiant, the surface is not calm at all. It churns. Vast cells of hot material rise and cooler material sinks, creating irregular changes in brightness that can absolutely make a star look unstable. But irregular is the key word. Convection is good at producing noise. It is not especially good at producing a clean repeating pattern that lasts for generations of observation. A 6-year signal that keeps returning starts to feel less like surface weather and more like structure. Magnetic explanations ran into trouble for similar reasons. They were not impossible, they just were not satisfying. They tended to explain pieces of the puzzle without explaining why the same long-period signature kept reappearing with such persistence. And slowly, almost reluctantly, another possibility became harder to ignore. What if the 6-year rhythm was not coming from inside Betelgeuse at all? What if it was orbital? That idea changed everything. Because if the long secondary period was being produced by an orbiting companion, then Betelgeuse had not been misbehaving as a single star. It had been correctly behaving as part of a binary system that nobody had properly identified. That is a very different claim. Now the strange 6-year signal is no longer a failed stellar pulsation model. It becomes evidence, a footprint, a repeating signature of motion. And suddenly, the whole star starts to look different. A companion moving through or near the extended outer envelope of Betelgeuse could create exactly the kind of long-period effect astronomers were seeing. Not because it was shining brightly on its own, but because its motion through that vast atmosphere would disturb the gas, alter local conditions, and imprint a repeating rhythm on the system. The signal that once seemed annoying or ambiguous starts to make more sense the moment you stop forcing Betelgeuse to be alone. That realization did not arrive all at once. It emerged slowly, because astronomy rarely gives up its secrets in a single dramatic moment. More often, the evidence accumulates piece by piece until the old explanation begins to collapse under its own weight. That is what happened here. Researchers revisited older photometric records. They looked again at brightness changes that had been catalogued for decades. They compared those records against newer observations, better instruments, and more advanced models of how giant stars should behave. And the more carefully they checked the long secondary period, the less convincing the old internal explanations became. Then the implications widened, because the 6-year signal had not just been sitting in the data as a mystery. In some cases, it had been used as an input for modeling Betelgeuse itself. If you assume a repeating period belongs to the internal structure of a star, you can use it as a constraint. It helps define what the interior is supposed to look like. But if that same period is actually orbital, then those models are built on a false assumption. The input was misidentified. And once that happens, everything downstream has to be reconsidered. This is where the story becomes genuinely fascinating. The binary interpretation does not just add a companion star to the picture. It forces astronomers to rebuild the picture from the ground up. If the 6-year period belongs to Sawara's orbit rather than Betelgeuse's internal oscillation, then some earlier estimates of the star's internal structure become less secure. Some models of its remaining lifetime shift. Some assumptions about how close it is to its final collapse may need to be adjusted. Ironically, that means Betelgeuse may be slightly less advanced in its nuclear clock than some earlier interpretations suggested. But at the exact same time, the system as a whole may be in much greater danger. That sounds contradictory until you separate the two clocks that are now running inside this story. The first is the nuclear clock. That is the normal life cycle of the star itself, the slow burning of fuel in the interior, the long countdown toward core collapse. The second is the inspiral clock. That one belongs to the companion. Sawara does not care how much fuel remains in Betelgeuse's core. It is losing orbital energy mechanically through drag as it moves through the giant's outer atmosphere. That process follows its own timeline. It is governed by gas density, gravity, and orbital decay, not by the star's nuclear burning stages. And that clock may be moving faster. So now Betelgeuse is no longer a star with one ending. It is a system with two possible countdowns happening at the same time. One says, the star may still have more time internally than we thought. The other says, the companion may force the ending much sooner anyway. That tension is what makes this system so extraordinary. The discovery does not simply tell us Betelgeuse is closer to exploding. It tells us the route to that explosion may be completely different from the one astronomers had in mind for decades. And once researchers started entertaining the orbital explanation seriously, more pieces of the puzzle began to line up. The 6-year period was not the only clue. Betelgeuse had also shown signs of motion that were difficult to interpret cleanly as the behavior of a perfectly solitary star. There were hints of wobble, subtle shifts, small irregularities that on their own might not have been enough to prove anything. But alongside the repeating long-period brightness signal, they stopped looking accidental. Individually, each clue could be dismissed. Together, they started forming a pattern. That is often how major changes in science happen. Not because one impossible piece of evidence appears, but because too many small things begin pointing in the same direction. The old model becomes harder and harder to defend, not because it was absurd, but because it gradually explains less and less. And the new model starts doing something the old one could not. It starts making sense of the whole system at once. Under the binary interpretation, the 6-year cycle is no longer mysterious. The atmospheric disturbances become more understandable. The long-term orbital decay becomes physically plausible. And Betelgeuse stops looking like a weird single star with unexplained habits and starts looking like something rarer, more unstable, and far more consequential. A common envelope system in progress. That phrase matters more than it may sound. A common envelope phase is one of the most violent relationships two stars can enter. One star expands so dramatically that it engulfs the other. The smaller companion does not remain safely outside. It ends up moving inside shared gas, where drag drains its orbital energy and pulls it deeper inward. Once that begins, the system changes from the inside out. Energy is deposited into the envelope. Angular momentum is redistributed. Mass loss can increase. The structure of the outer layers can be altered. The future explosion, when it eventually comes, may no longer resemble the clean textbook death of a lone red supergiant. That is why the 6-year signal matters so much. It is not just a timing anomaly. It may be the first unmistakable rhythm of a star being consumed from within. And if that interpretation is right, then astronomers were not merely looking at variability. They were watching the surface signature of an engulfed companion slowly falling deeper into one of the brightest stars in the sky. That is a very different kind of observation. It means that for over a century, the system may have been telling us exactly what it was doing, but in a language we did not yet know how to read. Now we do, or at least we are beginning to. And that shift in understanding leads directly to the next question, the one that makes this story even more unsettling. If Suara is really there, and if the 6-year cycle is the mark of its orbit, then how long does it have before the orbit collapses beyond recovery? How much time is left before the inspiral becomes a plunge? And what would that final descent actually do to Betelgeuse when it reaches the deeper layers of the star? That is where the story turns from hidden evidence to irreversible. 2 clocks are running inside Betelgeuse. Once astronomers began taking the hidden companion idea seriously, the story of Betelgeuse changed in a way that made the system far more unsettling. Because now there were not one, but 2 countdowns running at the same time, and they do not agree. The first countdown is the one astronomers have talked about for decades. It is the nuclear clock, the normal life cycle of a massive star. Betelgeuse is burning through its fuel in layers deep inside its interior, moving step by step toward the final core collapse that will one day destroy it. That is the familiar story, the textbook story, the one built from generations of stellar evolution models. If Betelgeuse were truly alone, that clock would dominate everything. Astronomers would estimate how much fuel remained, how the internal burning shells were evolving, how close the core was to instability, and from that, they would build a picture of how much time the star had left. Maybe a very long time by human standards, maybe much less by the standards of stars, but still one clock, one ending, one path forward. But Betelgeuse may not have that luxury anymore, because a second clock has started ticking inside it. That second clock belongs to Suara, not to nuclear burning, not to the deep interior of Betelgeuse, not to the slow fusion-driven life cycle of a red supergiant. This clock is mechanical, orbital. It is driven by drag, by friction, by the simple brutal fact that a star moving through gas cannot keep its orbit forever. Every time Suara moves through the extended atmosphere of Betelgeuse, it loses energy. Every loss of energy tightens the orbit. Every tighter orbit pushes it deeper, and every deeper pass means denser gas, stronger drag, and faster decay. That is the second countdown, the inspiral clock. And according to the picture emerging from the research, it may be running much faster than the nuclear one. This is where the story becomes genuinely strange, because both clocks are real, both are grounded in physics, and both may be telling the truth at the same time. One says Betelgeuse may still have a long internal future ahead of it. The other says the companion falling through its atmosphere may force the ending much sooner anyway. That sounds contradictory, but it is not. It just means the fate of the system is no longer controlled by a single process. For years, astronomers modeled Betelgeuse as an aging red supergiant approaching death through the normal sequence of late-stage stellar evolution. Those models are not nonsense. They are still physically meaningful, but they describe a star evolving on its own terms. Once you introduce an engulfed companion into the picture, the system stops being simple. Now the evolution of the star and the decay of the orbit begin interacting with each other. And that interaction is where the uncertainty explodes, because the 2 clocks are not fully independent. As Betelgeuse changes internally, the density structure of its outer envelope changes too. And that matters because the density of the envelope controls the drag Suara experiences. A denser path means a faster loss of orbital energy. A changing envelope means a changing inspiral rate. At the same time, the inspiral itself dumps energy into the gas, heating it, stirring it, and altering the outer structure of the star. In other words, the star affects the orbit, and the orbit affects the star. The two clocks are coupled. That is what makes Betelgeuse such a difficult system to predict. To model it correctly, astronomers would need to do something incredibly hard. Follow the long-term nuclear evolution of a massive red supergiant, while also tracking the orbital decay of a companion embedded inside its atmosphere, and then calculate how each of those processes changes the other over time. That is not one clean problem. It is several difficult problems stacked on top of each other. So for now, researchers are left with an honest and slightly unsettling conclusion. Betelgeuse has two futures running in parallel. One future is the classic one. The star continues burning fuel, moving slowly but steadily toward the collapse its core was always going to face. The other future is more violent. Suara keeps spiraling inward until the merger itself changes everything, either by restructuring the star, destabilizing it, or pushing it across a threshold earlier than nature would have on its own. That is the timeline paradox at the center of this story. The nuclear clock suggests patience. The inspiral clock suggests urgency. And right now, nobody can say with total confidence which one will win. That uncertainty is not a failure of the science. It is the science being honest, because astronomy is often presented as if every star has already been understood, classified, and placed neatly into a known category. But the universe does not always cooperate with that kind of simplicity. Sometimes it produces an object that sits right at the edge of what our models can cleanly explain. Betelgeuse may be one of those objects, a system close enough to observe, strange enough to challenge assumptions, and unstable enough that both its present and its future have to be reconsidered at the same time. And there is something almost eerie about that. For generations, people looked at Betelgeuse and saw a bright red star nearing the end of its life. That was dramatic enough, but now we may be looking at something even more compelling. Not a star waiting quietly for death, but a system already caught between two endings. One ending comes from the inside out, the other comes from the outside in. Deep in the core, nuclear burning keeps marching toward collapse. Far above it, inside the swollen atmosphere, Suara keeps falling. And both processes may be moving toward the same final chapter from different directions. That is why this is no longer just a story about when Betelgeuse explodes. It is a story about what pulls the trigger first. Will the star die according to its own internal timetable, or will the hidden companion rewrite that timetable before the natural ending ever arrives? That question matters because the answer changes everything downstream. It changes the likely shape of the explosion. It changes the structure of the material surrounding the star. It changes what astronomers should be looking for right now. And it changes how we interpret every strange signal Betelgeuse sends us from this point forward. So in practical terms, where does that leave us? It leaves us watching a star with two clocks and no final agreement between them. It leaves us with a system whose nuclear future may still stretch far ahead, while its orbital future may be collapsing much faster. And it leaves astronomers in the unusual position of studying one of the brightest stars in the sky while knowing that its true deadline may not be set by the star alone. That is the real shift in perspective. Betelgeuse is no longer just an aging red supergiant. It may be an active common envelope system in mid-descent, with a companion already buried inside it, already losing energy, already changing the star's fate one orbit at a time. And once you understand that, the next question becomes unavoidable. If the inspiral clock really is ticking faster, what exactly happens as Suara drops into denser layers? How does a common envelope system actually evolve? What does the feedback loop look like once drag, heating, and orbital decay begin accelerating each other? Because that is the point where this stops being a mystery signal in old data and becomes a physical process with consequences that can no longer the feedback loop that seals its fate. Now we get to the part of the story where the physics stops feeling abstract, because words like inspiral and orbital decay can sound clean, technical, almost harmless. But what is happening inside Betelgeuse is not harmless. It is not stable. And once you understand the mechanism step by step, it becomes very hard to imagine any version of this system escaping what comes next. Sawara is not simply orbiting Betelgeuse through empty space. It is moving through gas. That single fact changes everything. In empty space, an orbit can survive for immense stretches of time. If nothing removes energy from the system, the motion can continue. But Sawara is embedded inside the extended outer envelope of Betelgeuse, and gas does what empty space does not. It pushes back. Every time Sawara travels through that atmosphere, the gas exerts drag against its motion. That drag acts like a brake. It steals orbital energy. It steals velocity. And the moment an orbiting object loses even a little too much speed, gravity gains the advantage and pulls it inward to a smaller orbit. That is the first step. And if that were the whole story, it would already be serious enough. But the real danger is what happens next. Because once Sawara drops to a smaller radius, two things change immediately. First, the gravitational pull is stronger. A tighter orbit requires a higher orbital velocity to remain stable. Second, the gas density is higher. Betelgeuse does not have the same density at every depth. Like any giant star, its outer layers become denser as you move inward. So the deeper Sawara falls, the thicker the medium becomes around it. And that means the drag gets worse. More drag removes more orbital energy. More energy loss causes a faster orbital decay. Faster orbital decay sends Sawara even deeper. And deeper layers mean denser gas still. That is the loop, not a metaphor, not a dramatic exaggeration, a real physical feedback loop. Each step downward makes the next step happen faster. There is no natural point in this process where the system pauses, stabilizes, and says this is far enough. There is no restoring force that gently pushes the companion back out into safety. Once Sawara is inside the envelope and losing energy to drag, the system has crossed into a runaway sequence. That is why the phrase tipping point matters here. People use that phrase casually in everyday life, but in this case, it has a very specific meaning. A tipping point is the threshold beyond which recovery stops being physically plausible. The old balance is gone. The feedback mechanism takes over. The outcome may not happen instantly, but the direction of the system is no longer in doubt. And by this interpretation, Betelgeuse and Sawara passed that threshold already. The orbit is already shrinking. The drag is already active. The deeper descent is already underway. To picture it more clearly, imagine dropping an object into a thick fluid that becomes denser the farther down it goes. Near the top, the resistance is noticeable but manageable. The descent is slow. But once the object sinks lower, the fluid grows heavier and harder to move through. Resistance increases. The object loses speed more quickly. It drops faster into even denser material, where the resistance increases again. That is the logic of the system Betelgeuse may now contain. Sawara is not falling in one clean vertical plunge. It is falling through repeated orbits, each one slightly smaller than the one before, each one converting more orbital energy into heat inside the surrounding gas. And that conversion matters, because the orbit is not just shrinking quietly. As Sawara moves through the envelope, the energy it loses does not simply disappear. It is deposited into the gas around it. That means heating, stirring, disruption, and structural change in the outer layers of Betelgeuse. The companion is not just descending through the star. It is actively reshaping the environment it is moving through. So now the picture grows even more unstable. The gas slows Sawara down. Sawara dumps energy into the gas. That energy changes the envelope, and the changing envelope can alter the conditions of the inspiral itself. This is what makes common envelope evolution one of the hardest problems in stellar astrophysics. It is not just a two-body orbit. It is not just fluid dynamics. It is not just stellar evolution. It is all of those at once, with each piece affecting the others in real time. Researchers have to think about gravity, turbulence, gas density, heat transfer, orbital mechanics, and the changing structure of the giant star all together. That is why simulations of common envelope systems are notoriously difficult. especially in full three-dimensional hydrodynamic form. And that is also why Betelgeuse matters so much. Because astronomers may not just be modeling this process anymore. They may be watching it happen. That is an extraordinary possibility. Usually when scientists study common envelope evolution, they are looking at the aftermath, a compact binary, a system that has already merged. A gravitational wave source that carries the consequences of a common envelope phase millions of years after the fact. But here, with Betelgeuse, astronomers may be seeing the inspiral while it is still underway, while the energy deposition is still ongoing, while the orbital decay is still happening in real time. That means this is not just a strange story about one famous star in Orion. It may be a rare observational window into one of the key processes that shape some of the most extreme systems in the universe. Common envelope evolution is thought to play an important role in the formation of close compact binaries, merging neutron stars, certain black hole pairs, and some unusually energetic stellar explosions. If Betelgeuse really is a common envelope binary in progress, then it gives astronomers something invaluable, a nearby system where the process can be observed instead of only reconstructed after the fact. And that brings us back to the emotional center of the story, because it is one thing to describe this as a useful astrophysical laboratory. It is another thing to remember what that actually means. A star you can find in the sky with your own eyes may already be locked in a runaway decline. A companion star may already be trapped inside it. And with every orbit, that companion may be digging itself deeper into a denser, harsher, more inescapable environment. This is why the system feels so eerie. The ending is not happening all at once. It is happening by repetition, orbit after orbit, pass after pass, a slight loss of energy, a slightly smaller orbit, slightly denser gas, slightly stronger drag. Then again, then again, then again. From far away, Betelgeuse still looks familiar, just a red-orange star in Orion, but inside that swollen atmosphere, the physics may already be merciless. And once a common envelope inspiral reaches this stage, systems rarely find a way back out. That is the true meaning of the feedback loop. It does not need to be fast to be final. Even if the full merger still takes thousands of years, the outcome may already be decided. On human timescales, that sounds impossibly distant. On stellar timescales, it is the last chapter already underway. Estimates in the source place the remaining merger timescale on the order of roughly 9,000 to 10,000 years, which is effectively a blink for a star that has lived for millions of years. So the real shift in perspective is this. Betelgeuse may not simply be an aging red supergiant waiting for a supernova someday. It may be a system already committed to transformation, with a hidden companion falling inward through a feedback loop that no longer offers an exit. And once you understand that, the next question becomes impossible to avoid. If the inspiral is real, and if the feedback loop is already sealing Sawara's fate, then how do astronomers know the companion is really there? What moved this idea from an interesting interpretation to a serious working model? What evidence pushed researchers from suspicion to detection? Because that is where the clues that turned a theory into a case. Up to this point, the story of Betelgeuse has felt almost too strange to trust. A second star buried inside the atmosphere of a red supergiant, a hidden orbit, a slow inward fall. A common envelope system unfolding close enough for us to watch. It sounds dramatic enough that, under normal circumstances, you would expect astronomers to treat it with caution. And they did. Because this was never going to be proven by one strange image, one dramatic headline, or one isolated data point. It had to become a case. And that is exactly what began to happen. The shift came when several different lines of evidence, gathered in different ways and at different times, started pointing toward the same conclusion. None of them alone was perfect. None of them, by itself, could silence every objection. But together, they began to form something much stronger than a speculation. They began to form a pattern. The first major clue was the one astronomers had been staring at for more than a century without fully understanding it. That 6-year rhythm. The long secondary period in Betelgeuse's brightness had been treated for decades as an unresolved oddity, something likely internal, something probably tied to pulsation or convection or some other complicated behavior inside the star. But once the orbital interpretation entered the picture, the signal changed meaning completely. It stopped looking like a mystery inside the star and started looking like the repeating fingerprint of something moving through it. Then came the second clue. Betelgeuse was not only varying in brightness, it was also shifting in position on the sky, not by much, not enough for the naked eye or even ordinary observation to notice, but enough for careful measurements to reveal a subtle repeating wobble, one that matched the same long timescale as the brightness signal. In other words, the star was not just pulsing. Its apparent center of light was moving rhythmically, as though something massive were forcing the system to orbit around a shared center of mass. That is a familiar method in astronomy. It is how many exoplanets were discovered. You do not necessarily see the companion directly, you infer it from the motion it causes in the primary object. The planet pulls on the star responds, and that response can be measured. The same logic applies here. Except in this case, the companion is not a planet orbiting in clean, empty space. It is something much heavier, roughly 1.5 to 1.7 times the mass of the Sun, moving inside the diffuse, outer atmosphere of Betelgeuse itself. That changes the geometry, but not the principle. The wobble matters because it says the 6-year signal is not only photometric, it is dynamical. It is not just a change in brightness, it is motion. And once that became clear, the idea of a hidden companion stopped looking like an imaginative interpretation and started looking like the simplest way to connect the dots. But astronomy is a hard science, and astronomers are trained to distrust patterns that might still have easier explanations. So the next question was obvious. Could the companion be seen directly? That is where the story gets even better. In 2025, observers using the Gemini North Telescope applied speckle interferometry, a technique designed to squeeze high-resolution information out of rapid short exposures, even through the blurring effects of Earth's atmosphere. They were looking for a faint secondary signal in the immediate neighborhood of Betelgeuse, near where the orbital models predicted the companion should appear. And they found something, not a bright, clean star sitting alone in black space. Not the kind of image you could point to and say case closed, but a faint excess of light near the predicted orbital position. Exactly the sort of tentative signal you might expect if a companion were real, but buried in glare, partially lost inside noise, and seen under extremely difficult conditions. The significance was only about 1.5 sigma, which matters because 1.5 sigma is not a confirmed detection. In scientific terms, that is suggestive, not definitive. It is a hint, not a verdict. You would never build the whole case on that alone, but that is not what makes it powerful. What makes it powerful is where it appeared. It showed up near the position the orbital model predicted. That is the key distinction. It was not just random extra light somewhere in the field. It was a weak signal in the right place, consistent with the wobble, consistent with the 6-year period, and consistent with the broader picture of a companion embedded inside the envelope. That is how a theory begins to harden, not because one perfect proof arrives, but because every new piece of evidence lands where the model said it should. And the case did not stop there. The great dimming of 2019 and 2020, which at first looked like it might be the prelude to a supernova, turned out to be something else entirely. A massive surface ejection followed by dust formation. But the scientific legacy of that event was much larger than the explanation itself, because the dimming triggered an observational surge. Telescopes across Earth and in orbit turned toward Betelgeuse and collected an extraordinary set of data across multiple wavelengths. At the time, that campaign was aimed at solving the dimming event. Later, it became something even more valuable, a baseline, a detailed record of the star's atmosphere, brightness behavior, and velocity structure during an unusually well-observed interval. When astronomers went back through that data looking not just for dust, but for signs of a companion moving through the envelope, the archive suddenly became a gold mine. The Great Dimming did not reveal Sawara by itself, but it helped create the data set that made the inspiral model far more testable. That is one of the strangest parts of this story. A dramatic surface event that looked at first like a false alarm for supernova may have ended up giving astronomers the observational coverage they needed to expose a much deeper process already underway. And once that data was re-examined, more clues emerged. Ultraviolet observations traced asymmetries in the motion of gas across Betelgeuse's atmosphere. One side showed gas behaving differently from the other, and those patterns shifted in ways consistent with the predicted orbital phase of the proposed companion. In plain language, the atmosphere did not look like it was simply churning randomly. It looked like something was moving through it and leaving organized disturbances behind. That is the kind of evidence that matters because it links the invisible object to the visible environment. It is not just, there might be a companion. It is, the gas around the star behaves as though a companion is passing through it. That is a much stronger statement. By this point, the picture is no longer built from one clue, it is built from convergence. A repeating 6-year period in brightness, a matching wobble in position on the sky, a faint excess of light near the predicted orbital location. Atmospheric velocity patterns that shift with the same orbital logic, and all of those pieces point toward the same basic answer. Betelgeuse is not behaving like a solitary red supergiant. It is behaving like a common envelope binary with a companion already inside the star's outer layers. That does not mean every astronomer agrees the case is finished. They do not, and that is important to say clearly, because there are still objections, and some of them are serious. Betelgeuse is not a clean, quiet star. It is violently convective. Its surface is irregular. Giant cells of rising and sinking gas can create brightness asymmetries, shift the apparent center of light, and even mimic rotation under some conditions. In a system this turbulent, false positives are not a trivial concern. That means the wobble alone is not enough. The rotation signal alone is not enough. Even the faint light detection alone is not enough. But that is exactly why the multi-layered case matters. The objections weaken any single clue. They do not cleanly erase all of them at once. Convection is messy, but it does not naturally explain a clean 6-year periodicity repeating across more than a century. Surface turbulence can confuse astrometry, but it does not automatically account for phase-correlated atmospheric velocity patterns plus a faint signal near the predicted companion position. The skeptical view is real, and it deserves respect, but the total weight of the evidence now leans much more heavily than it did before. That is the real achievement of this stage of the story. Astronomers have not simply imagined a hidden star because the idea sounds exciting. They have built a working model that explains multiple independent observations better than the old single-star picture does. That is the difference between a dramatic hypothesis and a serious astrophysical case. And now that case leads to an even more extraordinary realization. If Sawara really is there, then we are not just detecting a companion. We are detecting a star inside a star. A substantial stellar object, still intact, still orbiting, still losing energy, still falling inward through the thinnest outer layers of Betelgeuse's envelope. Not a remnant, not a black hole, not a dead core, a real star hidden in plain sight inside one of the most famous stars in the sky. That is where the emotional center of this story shifts again, because the evidence no longer points merely to instability. It points to geometry, to scale, to a system so large and so swollen that another star can survive inside it for now, tracing a 6-year path through gas so thin it barely seems like a star at all, yet thick enough to seal its fate orbit by orbit. And once you really picture that, the next question becomes unavoidable. What exactly is Sawara? How can a star that massive still survive inside Betelgeuse at all? What does that orbit actually look like? How thin are the outer layers? A star inside a star. Now we get to the part of the story that is hardest to picture, because it breaks almost every instinct we have about what a star is supposed to be. When people hear that Betelgeuse may have a companion inside it, the first reaction is usually the same: that cannot possibly work. A star inside another star sounds less like astronomy and more like science fiction. But the reason it can work, at least for now, comes down to one crucial detail. Betelgeuse is enormous, and its outer layers are far thinner than most people imagine. Suara is not thought to be a tiny remnant or a dead compact object. It is a real star, likely somewhere around 1.5 to 1.7 times the mass of our Sun. In any normal setting, that would make it a major object in its own right. If you placed it at the center of our solar system, it would dominate everything around it. It would not be some dim, barely surviving ember. It would be the central star. And yet here, in this system, that same star may be orbiting inside Betelgeuse. To understand how that is possible, you have to understand the scale first. Betelgeuse is so large that its outer extent reaches far beyond what intuition is prepared for. Its radius is on the order of 700 to 800 times the radius of the Sun. If you placed it where our Sun is, its outer layers would stretch beyond the orbit of Jupiter. That means the distance from the core of Betelgeuse to the edge of its visible body is larger than the distance from the Sun to Jupiter. And Suara's orbit is estimated to be around 4 astronomical units from the center. That is roughly the region between Mars and Jupiter in our own solar system. So yes, the companion is inside Betelgeuse, but it is still very far from the core. It is moving through the star's extended outer envelope, not plunging straight through its dense interior. That distinction matters. It is the only reason this system can exist in its current form at all. Because the outer layers of a red supergiant are not like the solid, crushing furnace people imagine when they think of a star. They are extraordinarily diffuse. In some regions, the gas is so thin that by laboratory standards, it approaches what we would call a near vacuum. Not empty space, not harmless, but far less dense than the word star makes people expect. There is still enough material spread across a huge volume to glow, to scatter light, and to remain gravitationally bound. But it is tenuous enough that a companion can move through it without being instantly torn apart. That is the key to the whole geometry. Suara survives because it has entered the thinnest outskirts of an immense stellar atmosphere, a region diffuse enough to let it remain a coherent star. It has not been smeared into debris. It has not been vaporized on contact. It is still itself. But survival is not the same thing as safety. That is where the trap closes, because even an extremely thin gas is still a medium. And any object moving through a medium experiences drag. The drag may be weak at first, almost negligible on short timescales, but it never goes away. Orbit after orbit, Suara keeps cutting through that diffuse envelope, and each pass steals a little more orbital energy from it. That lost orbital energy is what matters. As long as a star has enough orbital energy, it can keep moving fast enough to remain in orbit rather than falling inward. But remove even a small fraction of that energy again and again over thousands of years, and the orbit begins to contract. The companion drops to a slightly smaller radius. That smaller orbit passes through denser gas. Denser gas creates stronger drag. Stronger drag removes energy faster. So the reason Suara is still intact is the same reason its fate is sealed. Betelgeuse's outer atmosphere is thin enough to let the star survive for now, but not thin enough to let it escape forever. That is what makes this system so eerie. It is not a sudden collision. It is not a clean plunge. It is a star surviving inside another star only because the outer envelope is so diffuse, while that same diffuse envelope slowly destroys the orbit one pass at a time. The medium is weak enough to preserve the companion in the present, but persistent enough to guarantee its death in the long run. And what Suara leaves behind as it moves is not silence. It leaves a wake, a disturbed trail of heated gas, a turbulent path through the envelope. The motion of the companion is not invisible to the surrounding star. Every orbit stirs the atmosphere, deposits energy into it, and changes the structure of the gas around the orbital path. In other words, Sawara is not merely surviving inside Betelgeuse. It is reshaping Betelgeuse from within as it falls. That is the true geometry of the system, not one star sitting neatly inside another like nested shells, but a massive companion moving through an immense, diffuse atmosphere, still coherent, still luminous, still gravitationally intact, yet already locked into an inspiral that grows more irreversible with every orbit. And once you really see that picture clearly, the next step becomes unavoidable. Because if Sawara is moving through Betelgeuse's atmosphere, it should not pass through quietly. It should push gas. It should stir the envelope. It should leave behind observable traces of motion. The wake written into the star. If Sawara is really moving through the atmosphere of Betelgeuse, then it should not be invisible in any meaningful physical sense. A massive object passing through gas does not move in silence. It pushes material aside. It compresses some regions. It leaves lower pressure regions behind. It stirs turbulence into the medium around it. And even after the object has moved on, the gas remembers. Not permanently, not perfectly, but long enough to leave behind organized patterns of motion that can still be measured if your instruments are good enough. That is the next step in this story. Not just the idea of a hidden companion. Not just the 6-year signal. Not just the wobble. But the possibility that Betelgeuse's own atmosphere is recording the passage of that companion orbit by orbit, and according to the data, that may already be happening. The key evidence comes from ultraviolet spectroscopy, especially observations gathered by the Hubble Space Telescope during and after the Great Dimming. Ultraviolet light is especially useful here because certain spectral lines, including lines associated with elements like magnesium and iron, act like traces of gas motion. When astronomers measure how those lines shift across the face of Betelgeuse, they can build a velocity map of the atmosphere itself. That matters because velocity maps do not just tell you that gas is present. They tell you where the gas is moving toward us, where it is moving away from us, and how those patterns change with time. And what those observations revealed was not a calm, symmetric atmosphere. They revealed asymmetry. One side of the atmosphere showed gas being pushed in one direction, while the other side behaved differently. More importantly, those asymmetries did not seem random. They shifted in a way that tracked the predicted orbital phase of the proposed companion. In other words, the disturbed gas was not merely chaotic surface weather. It looked organized, timed, structured by motion. That is a very different kind of clue, because now we are no longer just talking about a star that seems odd. We are talking about a star whose atmosphere behaves as if something is moving through it. That distinction is everything. Astronomers sometimes describe this kind of pattern as a dipole-like motion, an atmosphere responding unevenly across the stellar disk in a way that reflects a directional disturbance. The simplest analogy is a boat moving through water. The bow pushes water outward and aside. The stern leaves behind a turbulent wake. If you could somehow measure the velocity of every water molecule around that boat, you would not see randomness. You would see a complicated but meaningful pattern tied directly to the boat's motion. That is the picture the ultraviolet data suggests for Betelgeuse. Not literally water, of course, but gas. Not a boat, but a star-sized companion. Not a lake, but the extended outer atmosphere of a red supergiant. Yet the physical logic is strikingly similar. And what makes this so extraordinary is the distance involved. This is happening around a star roughly 650 light-years away. Astronomers are not watching a laboratory experiment from a few meters away. They are reconstructing organized gas motions in the atmosphere of a distant supergiant by reading tiny Doppler shifts in ultraviolet spectral lines. That is technically remarkable on its own, but what makes it far more important is that the pattern points in the same direction as the rest of the evidence. The long secondary period points there. The astrometric wobble points there. The faint imaging excess near the predicted orbital location points there. And now the atmospheric velocity field appears to point there too. That is how a case deepens. not because one piece becomes perfect, but because the whole structure begins to reinforce itself. If Suara is orbiting at roughly 4 astronomical units from Betelgeuse's center, then it should disturb the gas around its path. If it disturbs that gas, then the atmosphere should not remain symmetric. If the atmosphere becomes asymmetric, then high-resolution spectroscopy should reveal changing directional patterns. And that is exactly the kind of pattern astronomers now think they are seeing. This is where the hidden companion stops feeling hypothetical and starts feeling physical. You can almost picture it. Suara completes another pass through the thin outer envelope. Gas is compressed in front of it. Gas is dragged behind it. Heat is deposited along the orbital path. Turbulence spreads through the surrounding medium. Then the companion moves on, but the wake remains long enough to alter the atmospheric pattern that astronomers later observe from Earth. That is not direct imaging in the usual sense, but it is still a form of detection, a track, a disturbance field, a moving signature written into the atmosphere itself. And that may be one of the most compelling aspects of the Betelgeuse story. We may not be seeing Suara as a clean, isolated point of light, but we may be seeing what it does. The gas around Betelgeuse may be acting like tracer smoke around an invisible aircraft, making the hidden motion visible through the pattern it leaves behind. Of course, this is also the point where the skepticism becomes important. Betelgeuse is not a quiet star. Its surface is convective, unstable, and messy. Giant cells of rising and sinking gas can create asymmetries on their own. That means astronomers have to be careful. A strange velocity pattern is not automatically proof of a companion. Convection can imitate more than people expect, especially in a star as enormous and turbulent as this one. But here again, the problem for the single-star explanation is not any one clue by itself. It is the convergence. Convection may help explain some asymmetry. It may even mimic some wobble under the right conditions. But it does not naturally produce a century-long 6-year periodic signal, and then also line up neatly with orbital phase-dependent atmospheric disturbance patterns and a faint signal near the expected companion position. At some point, the companion model stops looking dramatic and starts looking efficient. It explains too many things at once to dismiss lightly. That is why the wake matters so much, because it moves the story from timing to mechanics, from signal to interaction. From there may be something there to the gas behaves like something is there. And once you reach that point, the emotional center of the story shifts again. Betelgeuse is no longer just a star with a hidden companion. It is a star being physically stirred from within. Its atmosphere may already be carrying the fingerprints of repeated orbital passages. Every loop of Suara's descent may be injecting energy, momentum, and disorder into the gas, slowly rewriting the envelope from the inside outward. This is not just a future catastrophe being prepared. It is a present transformation already underway. And that leads naturally to the next question. If Suara is depositing not only energy but also motion into the envelope, then could it be doing something even more dramatic than leaving a wake? Could it actually be spinning Betelgeuse up from the spin that shouldn't exist? There is another clue in this story, and unlike the 6-year signal or the atmospheric wake, this one feels almost impossible at first glance. Betelgeuse appears to be rotating too fast. Not a little too fast. Not by some tiny margin that can be shrugged away as measurement noise. Too fast in a way that suggests the standard picture may be missing a source of angular momentum entirely. That matters because red supergiants are not supposed to spin like this. As a star expands from a main sequence object into something as enormous as Betelgeuse, its rotation should slow dramatically. The physics is straightforward. It is the same basic principle you see when a figure skater extends their arms and begins to turn more slowly. The angular momentum is still there, but it is distributed across a vastly larger radius. And Betelgeuse has expanded to an absurd scale. A star that large should be turning very slowly by now, almost lazily, with an equatorial rotation speed under about 1 kilometer per second if it evolved in isolation. But that is not what the measurements suggest. Betelgeuse appears to be rotating at around 5 kilometers per second, and some estimates have pushed that higher, even toward 10 or 15 kilometers per second, though the upper end carries substantial uncertainty. Even if you take only the conservative value, the problem remains. 5 kilometers per second is still around 5 times faster than theory expects for a solitary red supergiant at this stage of its life. That is not a small mismatch. That is the kind of mismatch that tells you something may be fundamentally wrong with the assumption that the star got here alone. Because in an isolated star, there is no obvious mechanism to spin it back up. Expansion slows rotation. Mass loss usually slows it further. Time works against spin, not in favor of it. So if Betelgeuse really is rotating that fast, the natural question becomes unavoidable. Where did the extra angular momentum come from? And suddenly, the hidden companion model offers an answer. If Suara is orbiting inside Betelgeuse's envelope, then it is not only losing orbital energy to drag. It is also transferring orbital angular momentum into the gas around it. As the companion moves through the envelope, it drags stellar material along its path. That gas interacts with surrounding layers, and over time, the outer envelope begins to spin up in the same general direction as the orbit. In other words, Betelgeuse may be getting stirred from the inside, not by its core, not by some mysterious new internal engine, by a second star moving through its atmosphere, pulling and pushing on the envelope one orbit at a time. That is a striking picture. A star so enormous that another star can move inside it. And not just move inside it, but gradually torque it, transferring motion into the envelope until the outer layers begin rotating faster than a lone red supergiant should. If that interpretation is correct, then the spin is not just another oddity. It is another physical consequence of the inspiral. The wake disturbs the gas. The drag removes orbital energy. And the orbit also donates angular momentum to the star itself. That would make the rotation anomaly one more piece of the same larger machine. But this is also where the story has to stay honest, because the rotation evidence is not clean. There is a serious caveat here, and it matters. Betelgeuse has enormous convective cells, giant rising and sinking regions of gas across its surface. Those cells can create Doppler patterns that mimic rotation. If one side of the star has gas moving toward us, while the other side has gas moving away, the measurement can look like a rotating surface, even if the star is not actually spinning that fast at all. That makes this one of the most frustrating clues in the entire case, because the signal is plausible both ways. The rotation could be real, or part of it could be a convective illusion. And the frustrating part is that Betelgeuse is exactly the kind of star where that ambiguity becomes hardest to resolve. It is not a clean sphere with a quiet surface. It is a violently turbulent red supergiant whose atmosphere is constantly in motion. That means apparent rotation and real rotation can blur together under current observational limits. But even here, the key question is not whether one single measurement is perfect. It is whether the pattern holds up across the wider case. If the spin signal persists coherently across different epochs, that strengthens the idea that something real is being transferred into the envelope over time. If it shifts unpredictably from one observation to the next, that would point more strongly toward convection mimicking rotation. So the rotation clue sits in a very particular place in this story. It is not the foundation. The inspiral case does not depend on it. The 6-year period, the astrometric wobble, the faint excess near the predicted position, and the atmospheric wake already build the main structure. The rotation anomaly adds another layer, but it is a layer that comes with an asterisk. And yet that asterisk does not make it unimportant, because even if the full measured rotation turns out to be exaggerated by convection, the basic physical mechanism still exists. A companion embedded in the envelope should transfer angular momentum into the gas. That is not optional. That is part of the mechanics of the interaction itself. The only real question is how much of the observed spin is truly coming from that process and how much is being faked by surface turbulence. That is what makes this clue so compelling. It sits right at the boundary between detection and interpretation, between measurement and meaning, between a star that only appears to spin strangely and a star that is genuinely being spun up by an object hidden inside it. And if the latter is true, then the implications are hard to overstate, because now Betelgeuse is not just being disturbed, it is being mechanically altered. Its outer envelope may already be carrying not just the wake of Sawara's passage, but the rotational consequences of that passage as well. The companion is not only falling, it may be rewriting the motion of the star itself while it falls. That is an extraordinary thought. A visible star in Orion may be turning faster than it should because another star is inside it, trading orbital motion for rotation, converting one form of ordered motion into another as the system moves toward merger. And once you see that possibility, the next question becomes unavoidable. What if some of this evidence is misleading? What if the wobble, the spin, and some of the atmospheric patterns are not the signature of a hidden companion at all, but the illusion created by a star so turbulent that it can imitate a... What if it's an illusion? Every serious scientific story reaches the same uncomfortable point. The evidence starts to line up. The model starts to look elegant. The clues begin reinforcing each other. And that is exactly when the most important question has to be asked. What if we are wrong, not slightly wrong, fundamentally wrong? What if Betelgeuse does not contain a hidden companion at all? What if the wobble, the strange rotation, and even some of the atmospheric behavior are not the signature of Sawara, but the result of a star so turbulent, so irregular, and so enormous that it can imitate a binary system without actually being one? That is the strongest counter-argument in this entire story, and it is not weak. It is not something you dismiss with a dramatic sentence and move past. It is serious, technically grounded, and important enough that any honest account of Betelgeuse has to face it directly. Because Betelgeuse is not a smooth, quiet sphere. It is a violently convecting red supergiant. Its surface is not calm. It is alive with enormous cells of rising and falling gas, structures so large they can span hundreds of solar radii. These are not tiny ripples or minor imperfections. They are continent-sized disturbances on a stellar scale, huge regions of hotter and cooler material constantly shifting, swelling, fading, and reforming across the star's visible face. And that matters because telescopes do not measure a perfect geometric object. They measure light. If the brightness across the surface of Betelgeuse becomes uneven, then the apparent center of light can shift even when the star itself has not been pulled anywhere at all. To an observer making astrometric measurements, that can look alarmingly like a wobble. Not a real orbital wobble caused by a companion, but a false one created by brightness asymmetry on the surface of a single star. That is the heart of the skeptical case. The star may not be moving, the light distribution may be moving, and the same problem appears in the rotation measurements. If one enormous convective cell is rising on one side of the stellar disk, while another region is sinking on the other, the Doppler shifts across the surface can imitate rotational motion. One side appears blue-shifted, the other appears red-shifted, and suddenly a star that may be rotating very slowly can look as though it is spinning much faster than it truly is. So now the warning becomes clear. The wobble could be faked. The spin could be faked. And in a star like Betelgeuse, that is not some remote theoretical nuisance. It is a practical observational problem sitting right in the middle of the case. Hydrodynamic simulations have made that warning harder to ignore. They suggest that with current instrumental limits, a single convective red supergiant can generate apparent astrometric wobbles and apparent rotational signatures that resemble what astronomers might otherwise attribute to a companion. Some estimates go even further, suggesting that a large fraction of similar measurements on a convecting single star could produce false positives. In other words, if you look at a star like Betelgeuse under imperfect resolution, the physics of its own surface may trick you into seeing a binary system that is not really there. That is a serious objection. It means the wobble alone is not enough. It means the rotation anomaly alone is not enough, and it means the threshold for claiming a companion around a turbulent red supergiant has to be much higher than it would be for a quiet, stable star. This is exactly why the scientific community has not reached full consensus. Some researchers see the evidence for the binary model as compelling and convergent. Others look at each piece and argue that single-star physics can still explain it. The debate is real, active, and unresolved. That is not weakness. That is what science looks like when the data is difficult and the object under study refuses to behave cleanly. But here is where the skeptical case starts to lose its clean simplicity. It can challenge individual clues. It struggles much more with the full pattern, because convection, however violent it is, has a basic character. It is stochastic, messy, irregular. It produces variability, but not the kind of disciplined, repeating, clock-like behavior you would expect from an orbit. And that matters because the 6-year-long secondary period in Betelgeuse has been present across more than a century of independent observations. That is a very long time for a purely convective illusion to stay rhythmically coherent. That is the first major weakness in the single-star alternative. Convection can imitate noise. It is much worse at imitating a long, stable clock. Then there is the atmospheric velocity evidence. The ultraviolet data do not just show general turbulence. They show asymmetric gas flows that appear to correlate with orbital phase. That is harder to dismiss as random surface behavior. Convection can absolutely disturb gas, but phase-linked asymmetry is a more specific kind of structure. It starts to look less like weather and more like interaction. And once you include the faint excess of light near the predicted orbital position, the skeptical alternative has to do something much harder. It has to explain not one misleading clue, but several independent clues that all lean in the same direction at the same time. The criticism remains valid for each piece taken alone, but the combined pattern keeps the inspiral model alive and for many researchers, arguably ahead. That is the real shape of the debate. It is not believers versus skeptics. It is not certainty versus denial. It is a contest between two explanations. One says Betelgeuse is a single red supergiant whose violent convection is fooling us in multiple ways at once. The other says Betelgeuse is a common envelope binary, and the different observations are separate glimpses of the same hidden process. Right now, neither side can claim absolute victory. That is important to say plainly. The case for Sawara is strong, but it is not beyond challenge. The convective counter-argument is serious, but it does not erase the long-period signal or the phase-linked atmospheric disturbances cleanly enough to close the case either. So for the moment, Betelgeuse remains suspended in one of the most fascinating states a scientific object can occupy. Not solved, not dismissed, but contested for good reason. And in a strange way, that makes the story even better. Because now the mystery is not just what is happening inside Betelgeuse. It is whether modern astronomy has finally uncovered one of the rarest phases in stellar evolution, or whether one of the most turbulent stars in the sky has constructed the most convincing illusion of a companion we have ever seen. That tension is what makes the next step so important. The case does not just need more theory, it needs better observation, something precise enough to separate orbital motion from convective deception, something sharp enough to decide whether the hidden star is real or whether Betelgeuse has been impersonating a binary system all along. The source points to a future observation window that may finally be good enough to do exactly the observation window that could settle everything. If the Betelgeuse story has reached a turning point, it is because the debate can no longer stay purely theoretical. The case for Sawara is now strong enough that the next step is not another elegant argument. It is a test, a real one, a geometric one, a moment in the orbit when the system should finally give astronomers their best chance, yet to separate a hidden companion from the blinding glare of the star surrounding it. That moment is expected to arrive in 2027, and the reason it matters begins with something very simple. Every orbit has a changing geometry. From Earth, A companion moving around Betelgeuse does not appear at the same position relative to the center of the star at all times. Sometimes it would be projected more directly against the face of Betelgeuse. Sometimes it would be hidden deeper in the glare. And sometimes, if the orbital model is right, it reaches the point where its apparent sideways separation from the stellar center becomes as large as it is going to get. That configuration is called maximum elongation. And for a system like this, maximum elongation is everything, because the core observational problem has never been just whether Sawara exists. It is whether it can be seen against one of the brightest, largest, and most overwhelming stellar backgrounds in the sky. Betelgeuse is not simply luminous, it is a giant searchlight. Any companion embedded within or near its outer atmosphere is trying to reveal itself while standing next to an object that dominates the entire field. That is why previous evidence has been suggestive rather than decisive. The 6-year period can be measured, the wobble can be inferred, the atmospheric wake can be mapped. A faint excess of light can appear near the predicted position, but direct confirmation remains brutally hard because the contrast problem is so extreme. At most orbital phases, trying to detect Sawara is like trying to see a candle flame inside a floodlight from miles away. Maximum elongation does not solve that problem completely, but it improves the odds more than any other point in the orbit. Instead of asking instruments to find a faint signal projected against the brightest possible part of Betelgeuse, astronomers get to look when the companion should sit at its maximum apparent distance from the center, where the primary star's dominating glare falls off enough to give that faint signal its best chance to emerge above the noise. That is why 2027 is not just another date on a chart. It is the date the geometry turns favorable. And unlike some distant astronomical event generations away, this one arrives while the relevant instruments already exist. The observational tools needed to attempt the test are not hypothetical. They are already operating. Some are already being used on Betelgeuse. The astronomy community knows this window is coming, and the level of attention directed toward it reflects how seriously the binary hypothesis is now being taken. To understand what astronomers will actually try to do, it helps to think in terms of two challenges. The first challenge is resolution. The second is contrast. Resolution asks, can we separate two nearby sources on the sky at all? Contrast asks, even if we can we detect the faint one next to the bright one? This is where the most powerful facilities become important. One of the most relevant is the Very Large Telescope Interferometer in Chile. It does not operate like a single conventional telescope. Instead, it combines light from multiple telescopes to synthesize a much larger effective aperture, which dramatically improves angular resolution. In practical terms, it can resolve incredibly fine structure, fine enough in some cases to study features on Betelgeuse itself. That makes it one of the strongest tools for searching near the predicted position of the companion during the 2027 window. Other large ground-based telescopes bring a second advantage through adaptive optics. Earth's atmosphere blurs incoming light. It is why stars twinkle to our eyes and why fine astronomical detail gets smeared before it reaches a detector. Adaptive optics systems correct for some of that turbulence in real time, sharpening the image and making it far more plausible that a faint off-center signal could be separated from the primary glare. In a case like Betelgeuse, that sharpening is not a luxury. It is the difference between a near-impossible search and a merely difficult one. And there is an important reason astronomers are encouraged by what has already happened. The Gemini North attempt in 2025 did not produce a confirmed detection, but it did produce something tantalizing, a faint secondary signal near the predicted orbital position at roughly 1.5 sigma significance. That is nowhere near enough to declare victory. It is not a discovery threshold. It is a hint. But it is a hint in the right place, under less favorable conditions than the geometry expected in 2027. That is why the upcoming window feels so consequential. The model has already made a positional prediction. A weak signal has already appeared near where that model said it should. Now the orbit is moving toward the geometry where the same prediction should become easier to test. In other words, this is no longer a vague hope that better telescopes might someday help. This is a concrete opportunity to ask a concrete question at a concrete orbital phase. If Suara is real, astronomers should see evidence strengthen where the model says it should. If the signal fails to appear under those favorable conditions, the companion hypothesis becomes much harder to defend. That is what makes this such a rare and beautiful scientific moment. A disputed model is about to face a geometrically meaningful test, not just more interpretation, not just more debate. A real chance at separation between prediction and illusion, and the possible outcomes are genuinely dramatic. If astronomers detect a clearer companion signal at the predicted location during maximum elongation, the whole case changes. The 6-year period, the wobble, the ultraviolet wake, the spin anomaly, the asymmetric gas flows, everything that has so far formed a converging but contested picture would suddenly have a direct anchor. The hidden star inside the star would move from compelling inference to something much closer to confirmed reality. But if the window comes and goes without a corresponding signal, that matters too. It would not erase every previous clue overnight, but it would force the model into a harder position. The convective illusion argument would gain strength. The faint 2025 excess would look more fragile. And astronomers would have to confront the possibility that Betelgeuse has indeed been constructing one of the most convincing false binaries ever seen. So 2027 is not important because it promises certainty in a magical sense. It is important because it offers leverage. It gives the field its best chance yet to push the system into a configuration where nature itself becomes less ambiguous. And there is something fitting about that. For more than a century, Betelgeuse may have been telling astronomers the truth in fragments, a repeated period, a wobble, a wake in the gas, a signal half seen through glare. Now, after decades of being misread, the orbit may finally be bringing the hidden companion into the one position where the truth becomes hardest to hide. That is where the emotional center of the story shifts again. Up to now, this has been a story about evidence. Very soon, it becomes a story about judgment, about whether the sky gives us the one clean look we have been waiting for, about whether one of the most famous stars in Orion is really alone, or whether a second star has been buried inside it all along, waiting for geometry to find. The explosion may already be taking shape. If Suara is real, then the most important part of this story may not be the final merger. It may be what the merger is already doing to Betelgeuse long before that last plunge ever arrives. Because the hidden companion is not just falling inward, it is changing the star on the way down. Every orbit through the envelope costs Suara energy, that much we already know, but that lost energy does not vanish. It gets dumped into Betelgeuse's outer layers, and crucially, it is not deposited evenly across the whole star. The energy concentrates along the orbital path, meaning certain regions of the envelope are heated and disturbed more strongly than others. That detail matters more than it may sound, because once the heating becomes uneven, the mass loss becomes uneven too. A solitary red supergiant already sheds material through stellar winds, convection, and surface eruptions. But a companion spiraling through the envelope adds a directional bias to that process. Instead of a roughly symmetric outflow, you begin to get enhanced mass loss in preferred regions, stronger outflows along certain paths, and a circumstellar environment that becomes increasingly lopsided over time. In other words, Betelgeuse may already be building the shell that its future explosion will one day run into. And that shell may not be spherical at all. This is where the story changes from hidden companion mystery to supernova engineering. Because a supernova is not defined only by what happens in the core, it is also shaped by what surrounds the star when the blast wave finally arrives. If the star explodes into relatively clean space, the shock expands one way. If it explodes into a dense, pre-structured envelope of gas and previously ejected shells, the outcome can look very different, brighter, longer-lasting, and more asymmetric than a standard explosion in an unmodified environment. That means Sawara may not just affect whether Betelgeuse explodes earlier. It may determine what kind of explosion we eventually see, and there is real modeling behind that idea. Three-dimensional hydrodynamic simulations referenced in the source suggest that the inspiral of a companion in a system like this can eject a substantial amount of envelope material before the merger is complete, potentially on the order of half a solar mass or more. Not in one violent burst, but gradually through cumulative heating and orbital energy injection over time. Half a solar mass is not a cosmetic change. That is enough to create a serious circumstellar structure around the star. A shell, a set of clumps, dense asymmetrical regions, material that would still be waiting there when the final shock comes racing outward. And once you picture that clearly, the implications become hard to ignore. The future supernova of Betelgeuse, whenever it happens, may not be a clean textbook core collapse event. It may be an explosion shaped in advance by years, centuries, and millennia of binary interaction. The blast wave may not emerge into emptiness. It may crash into a medium that has already been pre-sculpted by Sawara's descent, a medium marked by asymmetric heating, enhanced outflows, and previously ejected shells distributed by orbital dynamics rather than by simple spherical wind loss. That is one of the most extraordinary aspects of this whole system. The star may already be writing the visible character of its own death, not in the core alone, in the envelope, in the circumstellar environment, in the material now being pushed outward by a companion that most people still cannot see directly, and some of the observational hints may already be there. Interferometric imaging at millimeter and submillimeter wavelengths has shown that the material around Betelgeuse is not cleanly symmetric. The circumstellar environment contains clumps, plumes, and asymmetric density structures that have appeared across multiple observing campaigns. On their own, those features do not prove the companion model, because convective ejection events can also produce asymmetry. But they are at least consistent with the idea that mass loss is being enhanced and organized in a directional, orbit-linked way. So again, the evidence does not point to one isolated miracle clue. It points to convergence. A companion orbiting through the envelope should inject energy unevenly. Uneven energy injection should drive uneven mass loss. Uneven mass loss should produce an asymmetric circumstellar environment. And Betelgeuse does, in fact, appear to sit inside an environment that is already clumpy, irregular, and far from perfectly spherical. That does not settle the case by itself, but it makes the larger picture more physically coherent. And coherence matters, because once a model begins to explain not only the orbit, not only the wobble, not only the atmospheric wake, but also the large-scale structure of the material around the star, it stops feeling like a narrow hypothesis and starts feeling like a full system description. This is also the point where the emotional center of the story shifts again. Betelgeuse is no longer just a star with a secret companion. It is a star whose future death scene may already be under construction. The explosion, whenever it comes, may carry the imprint of what is happening right now. The brightness, the asymmetry, the way the shock wave propagates, the way the circumstellar material lights up when the blast hits it. All of that may be shaped by the companion's current descent through the envelope. So the real meaning of Sawara may not be just that it is inside Betelgeuse. The real meaning is that it may already be transforming a normal stellar death into something much stranger. A supernova preconditioned by merger physics. A detonation whose appearance is being prepared long before the core ever collapses. And that leads directly to the next question. If the companion can reshape the envelope this much, could it also have influenced some of the dramatic surface events the Great Dimming revisited? By now, it is tempting to reinterpret everything Betelgeuse has done through the lens of the hidden companion. The 6-year signal, the wobble, the atmospheric wake, the rotation problem, the asymmetric mass loss. Once a model becomes powerful enough, it starts pulling every strange event into its orbit. And that is exactly why this next part has to be handled carefully. Because the great dimming of 2019 and 2020 is one of the most famous things Betelgeuse has ever done. And despite all the new ideas surrounding Sawara, the main explanation for that event is still solidly grounded in more ordinary stellar physics. What happened is now understood reasonably well. A large convective cell near the surface appears to have driven a major outflow of gas away from the star. That material moved outward, cooled in the outer atmosphere, and condensed into dust. The dust then blocked part of the light that would normally have reached Earth, making Betelgeuse appear dramatically fainter for a time. That sequence is not the controversial part. The surface ejection happened, the gas cooled, dust formed. The star dimmed. That chain of events is well supported by the observations and is not seriously disputed. So the important thing to say clearly is this: the great dimming does not need Sawara in order to be explained. It already has a credible physical explanation without invoking a hidden companion. But that is not the end of the story. Because once the binary interpretation enters the picture, another question becomes difficult to ignore. Not whether Sawara caused the dimming by itself, but whether it may have influenced the timing of the event. That is where the speculation begins, and it needs to be labeled honestly. Some researchers have noted that the 2019 surface mass ejection occurred during a period that appears consistent with a particular phase of the 6-year-long secondary cycle. In other words, the dimming happened at a time that may not have been random with respect to the proposed orbit of the companion. But that connection is not proven, and that matters a lot. Because correlation is not causation, especially in a star as turbulent as Betelgeuse. The surface is already driven by multiple overlapping processes at once: convection, pulsation, outflows, radiative effects, and large-scale atmospheric instability. In a system that messy, a dramatic event can line up with an orbital phase by coincidence. Still, the idea is not absurd. There is at least a plausible physical pathway. If Sawara passes through parts of the envelope where the gas density is slightly higher at certain orbital phases, then the localized energy it deposits there could produce pressure disturbances that travel through the surrounding material. Those disturbances might not directly create a surface ejection on their own, but they could bias the system, nudging it toward instability, making a major outflow slightly more likely at certain times than it would have been otherwise. That is a subtle but important distinction. Sawara would not necessarily be the primary cause. It might be more like a trigger, or even more cautiously, a biasing factor. A hidden influence that does not generate the event from nothing, but changes the odds of when and how such an event occurs. And that possibility fits the broader picture we have been building. If the companion is already stirring the envelope, heating some regions asymmetrically, transferring momentum into the gas, and leaving behind a wake, then it would not be surprising if those effects occasionally surfaced as visible disturbances in ways that look, at first glance, purely internal. That may be the deeper lesson of the great dimming, not that it proves Sawara, it does not, but that it reminds us the envelope of Betelgeuse is responsive, unstable, and capable of dramatic visible change. It is a star whose surface behavior can be shaped by processes happening underneath or within the outer atmosphere, even when those processes are not immediately obvious to observers. And in that sense, the dimming matters enormously. Because even if the event was fundamentally driven by convection and dust formation, it showed astronomers something critical about the system. Betelgeuse is not a passive giant sitting quietly at the edge of death. It is dynamically alive. It can launch major outflows. It can create large dust clouds. It can reorganize its visible appearance on surprisingly short timescales. That is exactly the kind of star where a hidden internal disturbance could be expressed on the surface without announcing its true origin. A star being stirred from within might not display that fact in a clean, labeled way. It might express it as a mass ejection, a dimming event, an atmospheric asymmetry, a temporary cloud of dust. Something that looks local, even if the deeper conditions helping to set it up were not entirely local at all. That is what makes the Great Dimming so valuable in this story. It is not the smoking gun for the companion hypothesis. It is something subtler, a proof of responsiveness, a proof that Betelgeuse's outer layers can react dramatically to disturbances, a proof that visible surface events and hidden interior or envelope dynamics may be more entangled than we assumed. And there is one more reason the dimming remains central. It triggered an enormous observational response. Because Betelgeuse faded so dramatically, telescopes across multiple wavelengths turned toward it. That created one of the richest modern data sets ever assembled for this star. Even though that campaign began as an attempt to explain the dimming itself, it ended up giving astronomers a far more detailed look at the atmosphere, outflows, and changing behavior of Betelgeuse than they might otherwise have had. That archive later became crucial for testing the binary interpretation more seriously. So, in the end, the Great Dimming may matter less as a direct clue to Sawara than as a gateway. It forced astronomers to watch Betelgeuse more closely, and once they did, the hidden companion story became much harder to ignore. That is the honest position. The Great Dimming is not definitive evidence that the companion triggered a surface event. But neither is it irrelevant. It sits in the story as a caution and an invitation at the same time. A caution against over-interpreting coincidence, and an invitation to consider that some surface events in a star like this may have deeper amplifying factors still hidden inside the envelope. Which brings us to the next, unavoidable step. If the inspiral is real, then eventually speculation gives way to destiny. The orbit will keep shrinking, the drag will keep increasing, the feedback loop will keep the final descent. At this point in the story, the question is no longer whether the inspiral is dangerous. It is. The real question is how that danger unfolds over time. Because what makes Sawara's fate so deceptive is that the process does not look dramatic at first. From a human perspective, everything still seems slow. The companion is still orbiting. The system is still intact. Betelgeuse still shines in Orion the way it always has. Nothing about it from the ground looks like a disaster already underway. But that calm is misleading, because the descent is not linear. And that single fact changes the entire future of the system. Right now, Sawara is thought to orbit at roughly 4 astronomical units from the center of Betelgeuse. That places it in a region of the star's extended envelope that is still genuinely diffuse. The gas is thin enough that the drag, while real, does not destroy the orbit immediately. The period remains on the order of 6 years, and the energy lost during each orbit accumulates gradually rather than catastrophically. That is why the system can appear almost stable from the outside, not because it is safe, but because it is still in the slower phase of the fall. And this is the part that matters most. A slower phase is not the same thing as a gentle ending. It is just the opening stage of a runaway process. If the inspiral were linear, the future would be relatively simple to imagine. Sawara would lose roughly the same amount of orbital energy on every orbit. The decay would proceed at a steady rate. The timeline would be long, predictable, almost mechanical, but that is not how common envelope inspiral works. The actual process accelerates. Each time the orbit shrinks, Sawara moves into slightly denser gas. Denser gas produces stronger drag. Stronger drag removes more orbital energy. More energy loss shrinks the orbit faster, and a faster shrinkage sends the companion deeper still. So the amount of energy lost per orbit does not stay constant. It grows. That is the key. The deeper Sawara goes, the more expensive each orbit becomes. In the outermost regions of Betelgeuse's envelope, the companion may complete many orbits while losing only a small fraction of its total orbital energy. But farther in, that balance begins to break. There comes a transition point in the intermediate layers where the inspiral stops feeling gradual and starts becoming dramatically more severe. That transition point is where the final descent truly begins. Above it, the system evolves slowly enough that the inspiral can look almost geological, something unfolding across long stretches of time with no obvious urgency. Below it, the entire logic of the motion changes. What was once a long orbit with modest losses becomes a tighter, harsher, more costly plunge through denser material. The feedback loop that has always been there stops whispering and starts accelerating the outcome with real force. That is why estimates of roughly 9,000 to 10,000 years to merger can sound deceptively calm. Those numbers describe the remaining time in the current regime. They do not mean the last stages will be spread out evenly across that whole interval. In fact, the opposite is more likely. The final few thousand years could be far more dynamic than the average rate suggests, because the late inspiral should speed up sharply as the companion descends into thicker and thicker layers. That is the trap hidden inside long timescales. People hear thousands of years and imagine slowness all the way through, but astrophysical systems often spend a long time preparing for an ending that becomes much faster near the end. Betelgeuse may be doing exactly that now. For most of the inspiral, Sawara survives because the outer envelope is diffuse enough to let it remain a coherent star. Later, that same geometry turns against it. The gas thickens, the orbital losses increase. The descent compresses into a much shorter final interval, and eventually, the environment ahead stops resembling an outer atmosphere at all, because the core region of Betelgeuse is not like the tenuous envelope Sawara is moving through now. It is denser, hotter, and structurally much more severe. When the companion approaches that boundary, the nature of the interaction changes qualitatively. This is no longer just a star gliding through thin gas and slowly bleeding energy away. It becomes something far closer to a collision in slow motion, where the forces rise to an entirely different level. That is why the final descent matters so much. It is the stage where time stops behaving intuitively. The orbit does not fade out gently. It tightens, it accelerates, it becomes more unstable precisely because every step downward makes the next step happen faster, and emotionally, that may be the strangest part of the whole story. Betelgeuse still looks familiar to us because we are seeing it during the early, slow visible phase of an ending whose last act belongs to a different tempo entirely. Right now, the system still has room, still has distance, still has the illusion of patience, but built into that patience is a future plunge, a point where the remaining descent no longer unfolds like a long fade, but like a process finally reaching the layers that make delay impossible. So the truth is not that Sawara will someday start falling. It is already falling. The truth is that someday it will start falling faster. And once that shift happens, the journey to the bottom may compress from a long orbital decline into something much more violent in character, even if it still unfolds on timescales larger than a human life. That is where this part of the story, the moment of impact. At some point in the future, the slow part of this story ends. The long 6-year rhythm ends. The wide orbit ends. The illusion of patience ends, because Sawara does not keep circling forever. It keeps falling until it reaches the dense interior of Betelgeuse, and when that finally happens, the entire meaning of the system changes in a moment. Up to now, the inspiral has been a story of drag, orbital decay, wakes in the gas, asymmetric heating, and mass loss spread across thousands of years. But the merger itself is something else entirely. It is not just one more orbit in a long sequence. It is the point where separation stops being physically possible, and the energy involved is enormous. By the time Sawara reaches the boundary of Betelgeuse's dense interior, it has spent millennia converting orbital energy into heat and motion throughout the envelope. But in the final stages, that process is no longer diffuse enough to remain a background effect. The energy deposition becomes sudden in consequence, violent in scale, and impossible for the star to ignore. What had been a long decline turns into a decisive event, and this is where the future branches, because once Sawara reaches the bottom, astronomers do not see just one possible ending. They see several physically plausible ones. The most dramatic possibility is the one that has haunted this story from the beginning. The merger itself could push Betelgeuse over the edge. Under normal circumstances, the star might have continued evolving on its nuclear timescale, slowly burning heavier elements until the core finally reached its natural collapse threshold. But the merger does not have to wait for that timetable. If the final plunge deposits enough energy into an already stressed interior, it could destabilize the deep structure and trigger collapse much sooner than the star would have reached on its own. In that case, the long inspiral would not just accompany the ending, it would trigger it. And if that happens, the resulting supernova would not be ordinary, because Sawara's descent would have spent thousands of years preparing the environment around the star. Enhanced mass loss, uneven outflows, dense shells and clumps of circumstellar material arranged in patterns shaped by the orbit. So when the final shock wave erupts outward, it does not expand into clean emptiness. It slams into matter that the inspiral itself helped create. That interaction could make the explosion brighter, longer lasting, and more asymmetric than a standard core collapse event. In that version of the future, Sawara does not simply die inside Betelgeuse. It pulls the trigger on the final explosion. That is one ending, but it may not be the only one. A second possibility is quieter in the moment, but in some ways even stranger. The merger could complete without immediately causing core collapse. Instead of triggering an instant supernova, the orbital energy and added mass could be absorbed into the star, redistributed through the interior, and leave behind a fundamentally altered object. Betelgeuse would keep living for a while, but not as the same star we see now. It would become a merged star, carrying the structure, mass, and internal consequences of two different stellar histories forced into one body. That matters because a merged Betelgeuse would not evolve like an ordinary red supergiant anymore. Sawara's mass, roughly 1.5 solar masses, would not be a trivial addition. It would change the pressure on the core, the burning timeline, the internal composition profile, and the way the final collapse eventually unfolds. The future supernova in that scenario would still happen later, but it would carry the fingerprints of the merger in its light curve, its spectra, and the geometry of its remnant. In a sense, the merger would still survive into the explosion, written into the ashes. And there is a third possibility, the hardest to model and the least certain. The nuclear clock could win after all. Betelgeuse might reach core collapse before the inspiral fully completes, exploding while Sawara is still somewhere inside the envelope, not yet merged all the way down. That would create an even stranger situation. A supernova occurring in a star already undergoing common envelope interaction, with the companion still caught inside the structure as the blast begins. The exact outcome there is much harder to predict, but it would almost certainly be unusual. So the honest ending to this story is not a single neat prediction. It is a narrowing set of violent possibilities. That is what makes Betelgeuse so compelling. The details remain uncertain, the direction does not. If the companion model is right, then the system is already committed to transformation. The orbit will not recover. The feedback loop will not reverse. The companion will not climb back out into a safe, ordinary binary orbit. Whether the final result is an immediate triggered collapse, a merged star that explodes later, or a supernova that interrupts the inspiral before the merger is complete, all roads lead away from the simple single-star story astronomers believed for so long. And that may be the real power of this whole mystery. For more than a century, Betelgeuse was treated as a familiar ending, a famous red supergiant nearing its final act. A star whose death would be spectacular but conceptually simple. Now it may be something far stranger, a star inside a star, a common envelope system in progress, a visible point of light in Orion that may already be carrying out one of the most consequential hidden interactions in modern astrophysics. That is why this story matters beyond Betelgeuse itself, because common envelope evolution is thought to lie behind some of the most extreme systems in the universe. Tight, compact binaries, unusual supernovae, and mergers whose descendants may later produce gravitational waves. Usually we study those outcomes after the fact. With Betelgeuse, we may be seeing the process while it is still happening. A nearby laboratory for one of the most transformative and least understood phases of stellar evolution. And emotionally, that leaves us with a final image that is hard to shake. Tonight, Betelgeuse still looks calm. It still glows over Orion's shoulder with that familiar reddish light people have looked at for generations. But inside that swollen atmosphere, if this model is true, another star is already falling, already losing energy, already changing the envelope, already shaping an ending that may one day appear in our sky as a supernova, unlike the one astronomers once expected. So the real meaning of the tipping point is not just that a process has started. It is that the system may already have crossed the threshold where the old future is gone. What remains uncertain is not whether nothing will happen. It is which extraordinary version of the ending we are going to get. And that is where we leave it. A star visible to the naked eye, a hidden companion buried inside it, a slow descent already underway. And somewhere ahead, whether sooner by orbital violence or later by nuclear fate, an ending that may already be in the process of being